Okay, so the first of the top 10 that we're going to cover is bad randomness. And this is otherwise known as nothing is secret on the blockchain. The contract code is public. The execution of contracts is deterministic. So everybody knows what transactions are going to do for the state of whatever that contract has on the blockchain. And an example of bad randomness sort of rearing its head is this random number generation. So typically, what's used in terms of generating random numbers, because this has to be deterministic, every full node needs to be able to get the same randomness. You use a pseudo-random number generator typically. So it looks random, but it isn't actually purely random. And this results in the ability for anyone to predict any of the random numbers generated in your smart contract. So here's a walkthrough of how a victim contract can be exploited by making this incorrect assumption. In this scenario, a victim contract uses the block number as a source of randomness for a game. So if you don't know any better, you might think that the block number is unguessable, but you can see it's just a number that increments. And that might be obvious to you, but there are smart contracts that are using this as their source of randomness. An attacker can create a malicious contract that checks to see if the current block number is a winner. So say you have a contract that uses the block number to determine a lottery winner, which we'll see in a bit. And the malicious contract is like, oh, well, I can figure out whether or not that block number is going to win or not, and then I can selectively play based on whether or not it is. And so if it is a winner, it calls the victim contract immediately in order to win. And then since the call is going to be in the same, it's going to try and make it so that it's in the same transaction as the winning block number, so that it can pull all the funds out of the contract. Okay, so it's just going to sit and wait to play until it knows it can win 100%. Okay. So that is an example. This happened in this smart billions contract, which is why smart is a misnomer when you say smart contracts, because this particular lottery had it so that if you correctly guessed 6 random numbers, you would get a payout of 70,000 times. So the contract developer put an initial amount of ether in there, and then it's just like a lottery. If you get up to 5 correct, you get 200 times. And if you get 6 of them, you get 70,000. And of course, this is the article, and this was 2 years ago, I think. So the hacker figured out what was the vulnerability in this smart contract, and was able to first win this minor prize 2 times, and then was about to empty out the contract with hit number 6, and then the smart billions contract developers had a backdoor, and they took the ether out before this thing could happen. So, and that's what you see. They withdrew the remaining 1,100 ETH immediately after realizing that in 5 minutes, and so we'll get to this time. You'll actually be exploiting the same vulnerability later on in this class, but they knew within 5 minutes they were going to lose all of their 1,100 ETH, so they had to go and withdraw it before the attacker withdrew it. So that's an example. Here's another example from this article from 2016. There was this contract called the Run that was using the block timestamp to generate random numbers and award a jackpot based on it. And this block timestamp you would think is random. This is the number of seconds in the epoch. So it's actually, there's a range of seconds that the block timestamp could be. But maybe if you take the hash of that range, maybe it'll give you some entropy. That's hard to guess. But as it turns out, if you're a miner, you control the actual time. You have some control over the timestamp value. And you can selectively pick a timestamp that will help you win this jackpot. And that's what happened with this particular contract. So some common errors before we get to code examples. Using known or predictable block variables as some kind of source of entropy is the real, it's the underlying issue here. So one source of entropy people think is block.coinbase. So Coinbase is the miner who has, the address of the miner who has mined the last block. So every block has a Coinbase block where, yeah, this is where this miner gets a certain amount of ether for mining this block. And that's their address. And so if you have a large diverse mining pool, maybe this is unpredictable. Maybe there's only maybe 5,000 different miners this could be. Block.difficulty. This is the difficulty of the puzzle that's solved, the difficulty level. This is actually known. It's known and deterministic and broadcast to all the miners. So this is not a source of entropy. The gas limit similarly. And you know, people are using these as a source of entropy, so this is why they're there. Block.number, which we talked about earlier, this is the current level or height in the chain, so that's well known. The block.timestamp, which was in the previous vulnerability, this is the wall clock time given in number of seconds since the epoch. That's well known. Even if you do something like this, block.block hash of the current block number, what do you think this will be?
It's just as deterministic as using the number itself, isn't it?
Yeah, it's even worse because it's basically 0. It's always 0. And it turns out the reason why it's always 0 is that because you don't really know a priori the block number as you're trying to execute the block to insert it into the blockchain. And this is where the complexity of what's going on underneath really hurts you, because a developer is going to be like, oh yeah, that should be just a real hash, right? But this will actually return 0. And if you've written this in thinking you're going to get some kind of random bit pattern, you'd be incorrect. So that's always 0. It's intended to be the block hash of the current block, but it's not known while executing your contract what your block number is. They don't want to take that into account in your context. And so you have to know as a developer that this is going to give you 0 every time. So now you all know. So yeah, hopefully you don't write any code that uses that. The block hash of the block number -1. So this is something that they do give you access to. The block hash of the previous block. The only problem with this is that it is known. Everyone knows what that block number is, so you can easily recalculate that as you like. Okay, worse. So the thing that's worse than that is what happens if you call this block.block hash on a block number that's more than 256 blocks old. What do you think you might get? So you also get 0. So it doesn't keep all of those block numbers around and it doesn't recompute them, so you end up getting 0. And so these are implementation issues that the language is not telling you about, right? And this is what the Smart Billions bug was that we saw earlier. This is how they knew that in 5 minutes they were going to get wiped out, because they were using the block.block hash of a particular block in order to see whether or not you won the lottery. And as it turns out, as soon as 256 blocks go by, that thing is 0. And if you had submitted a lottery ticket guessing all zeros, you would have won. And that is what the adversary did. The adversary did 00001 and then was like, only got the 200 times payout. And it was like, oh, sweet. If I guess all zeros, I'm going to get 70,000. Submitted all zeros and then matched was going to match all 6, but then they, within 5 minutes before that 256 block was minted, they took the money out. So you'll be I think the CTF level scratch card is basically you replaying this particular exploit. Okay. So here is some code examples of people using. I don't know if these. I think these are doctored, but they're derived from actual vulnerable code patterns. Here's an example of a smart contract. It has a private seed that everyone knows. And it's used in combination with an iteration number. And what it does is that it takes this random number as a hash of the seed and the iteration number. And then if the random number mod a certain number is 0, then you have a winner. Okay, so for this, if you know the iteration number based on the number of times people have played. So you can keep track of, on the blockchain, you can keep track of the iteration number. And you know the seed because even though it says private, the state is actually kept on the blockchain. So as an adversary, you can wait for a certain number of iterations, and as soon as you can find the random number, as soon as this random number, which you can calculate on every iteration, as soon as that n-1 transaction happens, where the nth one is the winner, you can immediately go and submit that transaction. Moreover, if you're the miner trying to win this thing, you can suppress everyone else's transactions and then only include yours as the one that wins. So that's the fundamental problem here. Okay. Okay, here's another one. The block.block hash is used to generate a random number using the current block number. The value is 0. So if you have something like this, which 0 mod whatever is always going to be 0, then it's basically the first caller who will be able to take all of the money out of this smart contract. Okay. Here's another one. Block.coinbase, block.difficulty, and the message.sender is used to generate the random number. So you can see there's a seed here that's derived off of Coinbase. There's a seed here derived off of the sender. The seed 3 is a difficulty, and then you take a hash of all of that stuff, and then the winning number is the hash mod, the total number of tickets. So all of this is, the data sources are public, so block.difficulty is public, or they can be manipulated directly by a miner. And if a miner wants to play this game, then basically the miner has the advantage over any of us who aren't a miner and who aren't running a full node. And so they can manipulate the Coinbase. They know the Coinbase. They can manipulate it. So if you're in a mining pool and the mining pool has a bunch of wallets that it uses whenever the miner wins the block or mines the block, it can fund the ether to a bunch of wallets. It has all of these different wallets that it can choose to be the Coinbase for. And so there is some control over the Coinbase and the sender, so then you would be able to have an advantage in this game. Okay. So there is some remediation, but this is something that is being worked on. Like, how do you get random oracles onto the blockchain, like truly random oracles that can't be gamed? One thing that you can think of is this in cryptography. There's this protocol called bit commitment, where you have just an example. I have a random number. You have a random number. We take the SHA hash of the random number and we publish those to the blockchain. And then later on, after we've committed, that's our commitment to the random number. Later on, in the next round, we both reveal our random numbers. And based on maybe we'll do a modulus or something like that. We'll use some combination of the original input. So we'll reveal the original input. We'll validate that hash was our commit. Like when you hash that input, it gives you the thing you committed to. And then from there, you generate your randomness, right? So then there's no collusion. But if you do this bit commitment protocol, the loser, because as soon as you reveal the numbers, as soon as the first person reveals the number, the second person can figure out already whether or not he or she is lost, and then you can suppress your reveal part of the protocol. In which case, you have to be smart enough to penalize such behavior. So this is just an example of things that you have to put on top of a blockchain in order to get something simple that we take for granted in computer science, things like random numbers. Okay, this is why games are hard on the blockchain for this reason. Okay, so then I'm going to walk you through the next 3 levels. So these are 3 levels that exploit bad randomness: the lockbox level, heads or tails, and lottery. And I'll just do those in slides because I think it's pretty straightforward. So the first one is lockbox. And then I'll hopefully wrap up in time for you to actually do these levels in class. So this is the code for lockbox. And you can see as part of the constructor, I have this pin code that is basically now mod 10,000. So this is the current block timestamp. Mod 10,000 is my pin code to unlock the lockbox. And of course I want to make it private because I think I'm going to hide it from people. And then the unlock function just takes the pin code that you send unlock and sees if they're equal to each other. And if they are, then you can get the balance back. Okay? So we already know that we can get this pin code, and moreover, we actually know what the block timestamp is. We have to look at the transaction that created the lockbox, and we have to go onto the Blockchain Explorer to see the timestamp of the block that included the contract creation transaction here. So that's what we'll do. So we'll go to the contract address in lockbox, which is up there. We'll look that contract address up on Etherscan. And on Etherscan, you can see this is the contract address here, and then in the bottom, or towards the right, you'll see that the contract creator, this is the lockbox level launcher address. You can see that address created this contract at this transaction. So we want to see what the block timestamp of this transaction is. So we'll click on this, and then this is what you'll get. You will get that when I created this contract on this hash, you'll see that my wallet sent the CTF game contract 0.1 Ether, and then this thing funded the level launcher to create the actual contract, which you'll see here. So you see the level contract is 860D9. You can see right here the final transaction here is the level launcher funding this 860D9 contract. And this is the contract that shows up in the UI. And so what you want to do is you want to figure out, well, when this contract creation happened, which is this last line, what was the block timestamp? Well, the block timestamp is right here. April 29th, so I did this in the spring. That's where these screenshots are from. April 29th, 2019. And so that is the Unix timestamp, but I need the seconds from the epoch. So there are multiple ways of converting that timestamp to seconds from the epoch. On a Unix machine, you could just do this up here, date-d, and then you give it this string plus %s, and then you'll get the number of seconds in the epoch. And you take that mod 10,000, which is basically the last 4 digits, 5316, and then you access the contract, copy and paste the ABI, call unlock, and the pin is 5316, and then you'll win. There is a link if you don't want to use date on your Linux machine. I think if you go through the lab walkthrough, there's a link to yeah, everybody's got a site that does something. So this thing will take your timestamp and unixtimestamp.com, and then you can enter you can enter your timestamp in. Yeah, so yeah, you can do either one. Will work. Okay. So that is lockbox. Should take you a couple minutes to actually solve. The next one is heads or tails, and this is the level that requires you to actually deploy a contract to attack the level. The heads or tails contract is a coin flipping contract, and you win the money from your level if you can get 10 more correct guesses than incorrect guesses. So it's just the law of probability forces you to you have to cheat the game in order to get your money back. But the result of the coin flip is determined by the last bit of block hash of block number -1. And so we already know this is not random. So this is the contract code, and you can see to play the game, you hit play with your guess whether or not the coin flip is either heads or tails. And this will be a Boolean. If you send true, you say it's heads. If it's false, it's tails. And then this contract takes in some money, and then it calculates some entropy. It gets the entropy as the block hash of block number -1, and then it calculates the coin flip as the entropy, the last byte of the entropy, logically ended with 1. So this just takes the last bit of that particular byte. So this is going to give you either 0 or 1 based on the coin flip. And if the coin flip, if the last bit is 1, this is a heads. And if you guessed heads and the coin flip is 1, then you get your money. If the coin flip is 0 and you guessed not heads, you get your money. So if you can win this 10 times in a row, you'll get all of your money back, is the idea of this contract. Okay? The idea of this contract is that it was hoping that the recent block number was going to be something that was hard to guess. Like, it's hard for you to figure out which block you'll actually be included in, because there is some delay before you submit a transaction, and then you're not quite sure which block you're going to get deployed in. But a program that is deployed in the same block or a program that's deployed that uses the block number -1 can programmatically access the value of the previous block. And so this is where you can always guess right, because you'll have exact information when the thing gets executed. And so what we're going to do is we're going to deploy an attacking contract in Remix that will programmatically access that value and send in the right value. Okay. So in order to talk about ways of deploying attack contracts or calling contracts from other contracts, I'm going to go through 3 different ways to do this, from the hardest to the easiest. And I want to stress that you're going to be doing the easiest. But this is just to show you what is going on underneath the hood in Ethereum. So the 3 ways to call your level contract from an attacking contract are these 3. So the first way, the ugliest way, is to go to the low-level call using the hash of the signature of the function you're trying to call. So in Solidity, and this is the reason why you're copying and pasting the ABI, because what it does is it goes to the function call interface, and it does a SHA-3 hash of every single function call, and it uses the first 4 bytes of that hash to determine which function to execute on the contract you're trying to call. So this is an example. If you have this play, which takes a Boolean, then the thing that gets sent in a transaction is the first 4 bytes of the SHA-3 hash of this thing. And that's how you attach this in your transaction, and that's where the smart contract knows which function you're trying to call. So these 2 things are equivalent. You could actually say, hey, I have a victim that I want to issue a call to. I want to send that victim 0.1 ether. That's part of my coin flip. And I can just send, as part of my payload, the first 4 bytes of that hash. And this will execute just exactly the same as this thing, which is doing, it's basically the last 4 bytes of this kekek hash. Or I think it's the first 4 bytes. So this is the ugliest way. This is the way you should not be calling, but this is just showing you that it's all just bits being sent across the wire. The second way to do this is to use the full source code of the victim contract that you're trying to call. And if you use the full source code, Solidity can figure out those hashes for you, right? So this is what you can do, is you can copy and paste the heads or tails smart contract into Remix, and you can get the full source code from the CTF itself. I'll show you a way to do that. If you do this, you could actually deploy the victim contract and your attacking contract on the JavaScript VM and then test there before you go and try and deploy it on the main blockchain. So here's an example. Say I cut and pasted the entire heads or tails contract into Remix. Then I can call it, I can instantiate it by calling this heads or tails contract on the victim address. So this instantiates a version of this contract that points to the actual address of the victim on the blockchain. And then I can just say, I want to call the play function in this using 0.1 ether, and my guess for heads or tails is going to be heads. I'm going to guess true. So that's another way to call this. And again, I don't recommend this way either, because that's cutting and pasting a bunch of stuff. But if you want to, you can click on the source tab of the CTF, and you have the actual source code of this contract. You don't need the CTF framework stuff, so you can delete that if you want to use this. In fact, you'll want to delete this, otherwise you'll have to supply the CTF framework code as well as the lockbox code. So then what you would do is you copy and paste this into your attacking contract, and then in your attacking contract you can directly instantiate the thing to call. The other way to do this is in the Mithril tab over on the right. You can download the source code of the contract using that button, and then you can copy and paste that into Remix. So again, I'm just showing you this as things you could do. I don't want you to actually do this. What I want you to do is to use the call function using the interface. I showed you this earlier, but this is just to reiterate that this is the easiest way to call into another contract. And so in this case, for heads or tails, I only really need to define the prototype of the function in heads or tails that I want to call. I can optionally add the authorized sender if I wanted to, but really you just want to specify that one. What you also have to do is when you deploy a smart contract, you also have to manually, so we have this authorized sender thing. When we deploy our attacking heads or tails, the attacking heads or tails is trying to interact with our original heads or tails, and it has to be registered as an authorized sender to that contract. So this, as you deploy your attacking contract and you get its address, you need to call this CTF challenge add authorized sender to make it work. So here's an example of the heads or tails exploit. This is just an image, so you can develop your own exploit. But if you look at this, I have this exploit call, and what I can do is I can exactly generate the coin flip state as I see in the original heads or tails contract. So I take the block hash of block number -1, that's my entropy. I take the coin flip to be that ANDed with 1, and then while the victim still has money, so this is the victim contract, I am just going to instantiate this interface and call the victim interface, which I haven't shown here, and I'm going to call play with the value of 0.1 ether, and I'm going to say I want to send true if this coin flip is 1, and otherwise I'm going to send false. And by doing this, I'm going to win every single time. And as soon as I've wiped out the victim contract, I can then just send all the money back to myself. Okay. So I have this contract. I compile it using the right version, 0.4.24. I can deploy the smart contract in Remix. I'll get this contract address, and then I'll need to copy this address. I need to go to the original contract address and then add this address as an authorized sender so that it can actually accept transactions. If you haven't done this, this is where you'll get the invalid transaction or out of gas error that I saw earlier in the on the Slack channel. And then you're all set. Then within Remix, you can just say, I need to, first of all, I have to send 0.1 ether because I have the contract asks you, if you recall this, in order to play the game, you actually need to send the right message value has to equal the cost, and the cost is the game funds div 10. So this is, I think this starts out with, how many ether does this start out with? Well, if it starts out with 1 ether, then each time that you play, the cost is 0.1 ether, which is, I think, what this is giving you. I'm guessing that it's 0.1 ether. So you have to fund the first coin flip. And then if you guess the first coin flip correctly, you'll get money back, right? And so then you only need the first one. Assuming that your contract is written correctly, you only need to fund the first coin flip. And then you can click exploit. So one of the things that you have to do in the exploit is make sure that the exploit is payable. Whoops. Oh, shoot. You have to make sure exploit is payable because you have to give it 0.1 ether so that it can then use that 0.1 ether to then call into the heads or tail contract. Okay, so then you hit exploit, and then when you hit exploit and you bring up that transaction, you will see this, where you have won. Actually, it's more than 10. But yeah, you've won all of the coin flips, and you can see the transfers happening from the victim to the attacking contract. I want you to show these in a level completion screencast, and then show the screencast of, or show the screenshot of the contract being cleared out. Are there questions about exploiting heads or tails? All right, so then the last one is lottery. And for this one, I'm not going to give you the code, but it's the same idea. You can see how the lottery tickets are generated, and you can just copy and paste that code into your attacking contract. And so it's very similar. For this one, I do want you to submit the attacker contract that you come up with in a directory within your Bitbucket, not Bitbucket. This is everywhere. Into lottery attack underscore, and use the exact same naming convention just for the sanity of Jeff. Okay, so that is it. I'm going to allow you to just work on all of those smart contracts levels right now. All right, unless are there any questions? Okay.